Swayam Prabha. Digital India. Educated India.
Hello and welcome back. So in this video we'll talk about Bayesian image registration. So far we have looked at methods like linear filtering, we saw boxcar averaging, we also looked at bilateral filter, etc. There we have assumed some prior knowledge about the noise in the image, right, which is basically zero mean additive noise. Expectation goes to zero, and we have expected that, especially in linear filtering. We have some constraint on the image in the sense we assume that it's locally constant, right? That's one way where we used averaging. So other than that, we have not used any constraints. So in the probabilistic framework, which is the Bayesian image registration framework, we are able to incorporate additional constraints on F. So for instance, smoothness constraints on F. Okay. So the idea here basically again for denoising is to determine an unknown function f from some observation g. So in this case the observation g is nothing but the noisy image itself, but it need not be. In some problems, for instance, g can be just a bunch of features that are related to the picture or the problem at hand. So for instance, it can be used for segmentation, classification, etc. Okay. So for the purposes of this topic, so we assume that g and f are vectors, which is what is given in block phase here. Block phase letters g and f, they are assumed to be vectors. So we rasterize the image, and so we have one big column vector. We will also refer to the individual elements of the vector as fi and gi. Okay. So the idea is to use Bayes rule. So we'll write down Bayes rule for this estimation problem. Remember, we are trying to estimate the denoised image f or the true ideal image f given the noisy observation g. So the probability of that, which is sometimes referred to as the posterior probability, is proportional to the likelihood p of g given f times the prior p of f. Okay. This p of g given f is basically called the data term. This is to make sure that that the image you estimate, the f you estimate, is not too far from g. So it should be consistent with g. So it's called the data term. P of f is the prior knowledge about f independent of the observation g. So this is not something that g is giving. This P of f is something that you are imposing. For instance, it has to be smooth, etc. Okay. So given this is the general framework for Bayesian image registration. So people get clever about making mostly by manipulating this P of f. This P of f is the prior terms or your knowledge of f that you want to impose. Is sometimes you can think of it as a regularization term. Okay, it's called, in the context of optimization, you can think of this as the regularization term. P of g given f is nothing but what is the the data fidelity term, that whatever f you are estimating, it should be consistent with whatever you have observed. That is, f is the denoid version of g, that should be meaningful. Okay. The conditional probability p of g given f, which is the data term, is characterized by some noise, right? That's another thing. So you are already incorporating noise here. So you are saying that g is a corrupted version of f, and we are also now making an assumption about the type of noise that is. And the type of noise you are assuming is that it is a zero mean Gaussian noise. So why do you call this the noise distribution? Because if you look at this expression, it's a Gaussian, but it's in this case since g and f are vectors, we have written it in this form with sigma being the covariant matrix. But f minus g, you can say f minus g is some epsilon, and so this becomes this expression p of g given f actually becomes 1 over z1 exponential of I'll leave out some of the normalization terms. So minus epsilon transpose sigma epsilon. Okay, so this is just f minus g. It's basically that's the noise, right? That's the noise. At every point, that's the noise. So you're just modeling the noise here. So you're also, and in the process, you're also saying what is the probability of G given a certain F, observing G given a certain F, because G is the noisy version. You are this probability distribution also defines, what the noise is. Okay, the Z1 is a normalizing factor for Gaussian distribution. Now, let's assume that if we assume that all the pixels in the image are independent of each other, okay, all the pixels in the image are independent of each other, and that is, we can draw each pixel from this distribution independently, and then they all have the same variation, and the equation we saw earlier simplifies to the following: P of G given F, we can write it as 1 over Z1 exponential of minus, there is a half which I'll take inside, so take outside here actually, I equal to 0 to n minus 1. So n pixels, Fi minus Gi squared by 2 sigma squared. So there is a summation in the exponent. So how did this happen? We are saying that all the pixels, we treat all the pixels independently of each other. So if you have an image, okay, the probability of getting that image, that noisy image G, is nothing but the product of the probabilities of the observing the individual pixels, right? So since this is an exponential distribution, the product adds up in the exponent, right? So if you want to rewrite this, I'll say product over I equal to 0 to n minus 1. What is the probability of observing the individual pixel? It's still an exponential distribution, minus 1 by 2. In this case, Fi minus Gi squared. Again, this is a sigma squared, right? This is for a pixel I. There are n pixels. So for observing the entire image, you multiply the probabilities, assuming that all the pixels are independent, right? So given two pixels, so if you know this rule, P of A and B together is P of A times P of B if A and B are independent events, right? So similarly, we can write this for the entire image, and this is, once again, the product adds up in the exponent, right? This is the exponent, so you can add up. So from here, you can get this expression. Okay, the a priori probability is modeled by another exponential distribution. So 1 over Z2, it's not Gaussian, but it's just an exponential, minus u of omega. Okay, this u of omega is often referred to as a potential, clique potential, or I'll just simply say it potential. Okay, so now if you let me write this down again, so that then we can write this. So we are using G and F as vectors. So if we write it down in terms of individual pixel values, what we can do, we can write down is that the probability of observing G given F is the true image, can be written as, there is some normalizing constant, the exponential, and it's the sum over all the pixels, that is 1 equal to 0 to n minus 1, Fi minus Gi raised to 2 by 2 sigma square. The probability P of F, right, we saw that the probability P of F is modeled as a it's also an exponential distribution. We saw it's some other normalization constant. It's exponential of minus u of w. Okay. So what is this u of w? Okay, this is often referred to as a clique potential. So clique potential is basically you are considering groups of pixels. Okay. So you can consider a group of pixels, and each of them can be called a clique, and for each group of pixels you have some you define some kind of spatial adjacency, and based on the spatial adjacency you also define these potentials. So for instance, one potential that is often used is u of omega. So I'll tell you what this is. U of omega is some beta summation over k equal to k minus 1 u of ik. Okay. So what is this? Where k is the number of cliques. So cliques is, given a neighborhood, into how many ways can you split them into pairs? 3 at a time, 4 at a time, etc. Like that's how we call it clique. And if you take every clique, okay, UK is the number of pixels, right? Pixels in a clique K, which has the same intensity as center pixel I. So you can consider like a square neighborhood, 3 by 3 neighborhood, right? And count, let's say I'll use different color. This is the center, these are same, maybe these are the same. Let's consider this whole thing as a clique, and maybe the others are slightly different. Right, different values. I'm just going to put a dot. So you can count the number of pixels which have the same value as the center pixel. Now what this does is to enforce smoothness. So you prefer images, right, that have in this case you prefer images which have a very a neighborhood, small neighborhoods with pixel values being almost the same. Okay, that's the smoothness, right? That's what you're enforcing with this kind of a potential function, right? So this is in terms of probability. So if for doing this, it's solving this problem is kind of hard because you see there are many arrangement of pixel values, correct? So and that becomes much harder to do. So one way you would solve this problem is you would you would actually formulate this P of f given G, which is what we saw there, right? So then at the beginning just write down how we are going to calculate f. That's more important, right? So calculation of f, so we will write it in individual terms. So P of G given f can be rewritten as this normalization constant time exponential minus I equal to 0 to n minus 1. This is the total number of pixels. N is the total number of pixels. Fi minus Gi squared by sigma squared. Okay. So in case you're wondering how we got here, what this assumes is that we treat each pixel as an independent random variable, right? In the sense, so if we choose a pixel, it is chosen with a certain probability from the distribution. You can think of it that way. The other way of looking at this is that the noise is Gaussian distributed. So that's why there's a summation in the exponent. So basically, if you start from the exponential distribution and you are modeling the entire image with this, so the probability of observing the first pixel will be times, if you use just this distribution, it will be f1 minus g1 squared by sigma squared, okay, times. So the probability of observing the entire image is nothing but the product of observing the entire, product of observing each of the individual pixels. So this is for pixel 1. Similarly, you can write this for 1/2, let's say, again, I'm going to not consider the other factors, f2 minus g2 squared by sigma squared, and of course we assume sigma is the same for all of the pixels. Like that, you can go all the way to exponential, there is minus sign here, minus fn minus g of n squared, in this case n minus 1 squared by sigma squared. So it's just a multiplication, right? For each pixel you have a term like this, and when you multiply you sum in the exponent, so that's why you get here. So for this you can ignore this product. If you want to write this particular expression in a compact form, you would write it in this fashion. So you would say product I equal to 0 to n minus 1. I put the 1 over z outside. Okay, exponential minus 1 by 2 fi minus gi squared by sigma squared. Okay, this is the probability. This is P of G given f. If we go pixel by pixel, right? So we take every pixel, for every pixel I, we estimate this probability, and then the probability for all the pixels put together, given that they are independently drawn, is just the product for each of the individual probabilities, right? So this is how we estimate this number, and if since it's an exponent, the product sums up in the exponent, so we get this expression. Okay, I hope that much is clear, right? So the fundamental assumption here is that the probabilities of the individual pixels are independent of each other, and they all have the same variance sigma square. Okay, and if you think of it that way, then this simplification can happen. Okay, so this summation of the exponent, right? We add one more here. Okay, so how do we define this P of F? P of F, as I stated, let me rewrite this 1 over some normalization constant time exponential of minus u of omega. Omega is not clearly written. U of omega is now can be written as beta times k equal to 0 to some capital K minus 1 u of ik. Okay, where k is the number of cliques. So cliques are basically how you in the context of this problem, let me rewrite this CLIQUES. So in the context of this problem, cliques are basically the neighborhood of every pixel, center pixel I. Okay, if I is the center pixel, you are looking at the neighborhood of that center pixel, and you can choose different kinds of neighborhoods. Okay, and each neighborhood you would call that as a clique. So in this particular case, UIK is the number of pixels in a clique K, which has the same intensity value as the center pixel. It's the same as center pixel. Okay. So if the neighborhood is the same, then the potential is always increasing. Okay. So consequently, you will have very strong. This will lead to very strong edges, because if you look at it, if there is a neighborhood which straddles an edge, right? So before that, let me draw some pictures so that you can appreciate this better. Let me just use a different color. So let's say a 3 by 3 neighborhood, right? So if there is an edge here, very strong edge going through here, having different pixel values, okay, and this is the center pixel, right? This one is the center pixel. Now the edge will have a considerably different value than the center pixel, correct? So then u will be lower, so this will be low if there is an edge around the center pixel, right? U will be low, so consequently P of F will be higher. So think of it that way, right? So having this, enforcing this constraint of having an increased potential whenever the cliques of center pixel have the same value as the center pixel leads to very strong edges. Okay. So the other assumption is the Markovian assumption or Markovian property, wherein you have for an image you will have there are n pixels, so each of them will have a neighborhood. So you will assume that each of those neighborhoods are independent of each other. Just as we assume that each pixel is independent of each other when we did the data fidelity term or the likelihood term, we assume for the prior term that each of these neighborhoods, the way we treat them, are independent of each other. So then we can still, when we consider each of the center pixels and we look at the entire prior probability, we just multiply that as well. Okay. So taking that all into account, we can rewrite this P of F given G as, change color, it's the we can write it in this form. I'll write down the last the final form so that you can work through the algebra yourself. Is this n minus 1 by 2 sigma squared. So minus this, again there is a minus and here I might have done a mistake on the minus sign, but let me correct it after I write it down. Okay, so we can close this. There are two, and have a small bracket here. So we want to maximize this probability, right? So that's the probability of the true image F given the noisy image G, that's posterior, and we want to maximize this. And in order to do that, we wrote it down as a product of the data term or the likelihood term. So and the prior, which now acts as a regularizer. Okay. So now we added the prior so that the probability of getting very strong edges are there. Okay, so the images will have very strong edges. The maximization of this probability actually means minimization of this exponent. So minimization of the exponent. So I equal to 0 to n minus 1. So we'll have the f I minus g I squared by 2 sigma squared, right, minus beta. This beta are just some hyperparameters that you will have to choose to make it work for the particular problem. Okay, so this is the loss function eventually that we are trying to optimize. So we have now made this into an optimization problem. There are many techniques for doing this optimization. One is called simulated annealing. Okay. The other one is called ICM technique. There is also a mean field annealing. Okay. The reason why there are so many techniques is because this optimization problem is hard. So for instance, that primarily comes from here, and of course the size of the problem is also big, right? Because we are trying to estimate Fi, pixel by pixel. Okay, and also this arrangement. So we're looking at clique potentials where we're just counting the number of pixels with similar values, right? So, but then the arrangement can be that leads rise to so many arrangements. Okay, and also depends on what the dynamic range of your image is. So the number of images here increases exponentially. So that way, the problem is harder to solve. We have to find the correct arrangement that satisfies this loss function. So there are many of these strategies are so-called greedy strategies to estimate this Fi. So remember, we want to estimate Fi. So that's the problem here. And we have started off from the Bayesian framework, figured out a data fidelity term or the likelihood term. We modeled this as a Gaussian. Of course, it's the same as modeling the noise as Gaussian. And we then had a prior. We imposed a prior, which is the same as regularization. Prior, of course, we can do lots of tricks there. That's where people work on. So what kind of prior will lead to a certain type of image. People work with that. So you choose a prior and then you write down the expression of P of F given G, which is basically trying to maximize this probability, right, for a certain image F. And when you do that in that process, you will end up with this optimization problem. Okay, that's what people typically solve in this line of research. Once again, I have presented this as some kind of pre-processing technique, but it's not exactly pre-processing, correct? There are so many people working on this as a research problem. It's been around for a long time. It's a difficult problem to solve. So this kind of Bayesian framework for solving these problems is generally a difficult problem to solve, and people have worked on this quite a bit. So this is a field of research by itself. But then if you are going to denoise pictures before using them downstream for other processing, maybe this is one method you can consider. Okay. So this ends this week's lectures on basic image processing techniques. Thank you.